Ever wonder how your phone's camera stabilizes a shaky video, or how a self-driving car decides when to brake? It all comes down to a tricky problem in control systems, balancing stability and adaptability in the face of uncertainty. Today, we're diving into a breakthrough that's making this possible. A new approach to teaching machines to make smart decisions using policy gradient methods and a clever trick called history representation. Let's start with the basics. Imagine trying to keep a broom upright on your finger. It's hard because tiny disturbances, like a breeze or a slight hand movement, can throw it off. Now scale that up to a drone in the wind or a robot navigating a crowded room. These systems have to deal with noise, unpredictable errors in sensors or the environment. That's where LQG control comes in. It's a classic framework for managing systems with noise, balancing two goals, keeping things stable and minimizing errors. But here's the problem. Traditional LQG methods struggle when the noise is too messy. The math gets complicated, and optimization algorithms can't reliably find the best solution. Enter policy gradients, machine learning techniques that let systems learn the best way to act by trial and error. Think of it like teaching a dog to fetch. You reward it for getting closer to the ball, and over time, it learns the optimal path. But here's the catch. Policy gradients work best when the system's rules are simple. For LQG, where noise is everywhere, the landscape of possible solutions is too jagged. It's like trying to find the bottom of a maze with no clear path. Your algorithm might get stuck in a dead end. So how do researchers fix this? They introduced a history representation, essentially giving the system a short-term memory. Instead of just looking at the current moment, the controller remembers past states and inputs. Imagine a driver using a GPS that not only shows the road ahead, but also the traffic patterns from the last few minutes. This historical data smooths out the optimization landscape, turning a maze into a hillside. Now the algorithm can roll downhill to the best solution, no matter where it starts. The magic. This approach makes the LQG problem gradient dominant. A fancy way of saying the math now reliably guides the algorithm toward the optimal controller. Researchers tested this on a tricky system, a pendulum balanced on its tip like a robot trying to stay upright. Even when the memory length changed, the method worked, proving its flexibility. Why does this matter? It's a game changer for real-world applications. From autonomous vehicles to industrial robots, systems can now learn faster and adapt better to uncertainty without needing a perfect model of the world. And the best part? The math shows that no matter how you tweak the history-based representation, you still end up with the same rock-solid solution. It's like different roads leading to the same mountain peak. Now let's zoom out. This isn't just about fixing one problem. It's part of a broader shift toward adaptive control. Think of it like a self-driving car that doesn't just follow rules, but constantly adjusts to traffic, weather, and even road construction in real time. Traditional systems rely on fixed programming, but these new approaches use machine learning to process vast amounts of data and make split-second decisions. How does it work? Researchers test these systems in simulated environments first, like digital labs where they can crash a virtual drone or stress test a robotic arm without real-world risks. Then they move to real-world trials, embedding these smart systems in everything from industrial robots to medical devices. The results? Systems that don't just react to problems but predict them. For example, a smart grid can forecast energy demand spikes and reroute power before outages happen. The findings are game-changing. These systems are up to 40% more efficient in complex tasks and reduce errors by over 60% in high-stakes scenarios. But the real wins. They're not just faster or more precise, they're safer. By continuously learning from their environment, they minimize risks in ways human operators alone never could. So what does this mean for you? It means the technology around us is becoming more intuitive, reliable, and responsive. Whether it's your smartphone adapting to your habits or a self-driving car navigating crowded streets, the future of control is about systems that grow with the challenges they face. Next time you see a drone soaring or a car navigating traffic, remember, behind the scenes, clever algorithms are turning chaos into control. Thanks for watching. Stay tuned for more deep dives into the science behind the tech, because the future of control is smarter, safer, and more adaptable than ever.